is the z-test. It is a measure of how far your sample's mean is from the mean of a normal distribution with a known mean and standard deviation. So here is formula for that. So z statistic. This here, this x with a bar over it, is called x bar. That is the symbol for a sample mean. And mu, the lowercase Greek m, that is the symbol for the population mean. You'll see this oftentimes, that the sample statistic is a Latin letter and the population parameter is a Greek letter. So up here we have the difference between what we actually observe and what we expect. And then we divide that by how variable the population is, because a difference up here is only really impressive if it's large relative to how variable the sample is. But then the bigger our sample size is, the more we really are confident that our estimate of the mean is pretty accurate estimate of the population mean. So z actually gets bigger when your sample size gets smaller. And this is the normal distribution showing. So basically we're going to be comparing that z statistic to the standard normal distribution of the mean of 0 and the standard deviation of 1. So that's what I just said. So here is the z statistic, and as the z statistic gets larger, we have a one-tailed probability. So this is a negative one-tailed probability. So our null hypothesis would be that the z statistic is greater than 0. And so the smaller our observed z statistic is, the lower the probability of observing that under the null hypothesis. And so the more willing we are to reject the null hypothesis and say that the research hypothesis is supported. Likewise, if we have a two-tailed test, then we're thinking that the sample mean is close to the population mean, and our actual z statistic has to be farther away from the population mean in order for us to consider it to be significant. So let's walk through an example, which hopefully will make more sense. So this first one, we're going to talk about ACT scores. So the original definition of the ACT described a distribution with a mean of 18 and a standard deviation of 6. And that's what's shown here in this red curve. And so school X thinks that its students are above average. Can we reject the null hypothesis that its students come from the population of typical students? So the research hypothesis is that school X's average ACT score is going to be greater than 18. So the null hypothesis would be that it's less than or equal to. So this is a one-tailed positive hypothesis. And so with an alpha of 0.05, we're going to need to see some kind of observation out here on the right-hand side. The average has to be out here for us to reject the hypothesis that these blue observations, which is school X's 20 students from school X, those are their ACT scores. So our critical value is 1.64. So if this was x-axis was standard deviations, like is up here, then they have to be 1.64 or higher, roughly almost exactly where the edge of my video inset is, hilariously. So, critical value is 1.64. If our z statistic is larger than 1.64, then we can reject the null hypothesis and we can say that indeed there is evidence that XU's students come from a population whose average is above the national average. So we find the mean of this group, and it's 17.75. The sample size is 20. So 17.75 minus 18 divided by the square root. There should be 6. That's the standard deviation. Divided by the square root of 20. That works out to be a z of minus 0.186. So it's less than one standard deviation below the expected mean, which makes sense, right? Because 17.75 is less than 18. So that since that z-statistic is less than our critical value of 1.64, we cannot reject the null hypothesis. In fact, our p-value is 0.426. So that means the probability of observing this z-statistic is like 43% of the time we'd expect to see a p-value this small, or smaller. So we have not found strong enough evidence to support the claim that students from school X are above average. Let's do another example. Once again, we're talking about ACT scores with a mean of 18 and a standard deviation of 6. So they scale the scores before they release them, so that's how we know what the population mean and the population average are. So now we've got students from a different school. And they're not making any claims about good or bad, but they do think that their students are not average students. And so what we're looking to do is reject the hypothesis that these students from school Y come from a normally distributed population with a mean of 18 and a standard deviation of 6. So again, alpha is 0.05. So the predictional research hypothesis would be that the students' average scores are either above or below. It's a two-tailed hypothesis. And so with a two-tailed hypothesis and an alpha of 0.05, the critical value for z is 1.96. So we have to compute. So let's calculate our z-statistic and compare it to this critical value. So mean ACT score of this group is 25.8. Sample size, again, is 20. So plug those numbers in, and you get 5.81. So this group is almost 6 standard deviations above the average. No, standard errors, excuse me, not standard deviations, standard errors. 6 times larger than we would expect from a sample of 20 students drawn from this typical population. So we can reject the null hypothesis because our z is greater than 1.96. In fact, the probability of observing a value this large, a z-value this large, if we drew 20 observations from a normal distribution with a mean of 18 and standard deviation of 6 is less than 0.001, which is really small. Typically, when we're reporting these tests, this is as small as a p-values you ever report. So that's pretty strong evidence that students from school Y are not average. In fact, they seem above average.